Today is that we're going to talk about manifolds. Sorry, let me just recap. So the plan for today is that we're going to talk about manifolds, and so I drew this sort of idea of the difference between topological spaces, manifolds, and metric spaces, and let's just revisit that idea at this point. So a topological space or topological spaces that we're looking at, those have to do, the idea of topological spaces has to do with the set X, okay, which are points in the topological space, but also a topology T, which is in some sense related to neighborhoods of points or all the sets that X belongs to, okay, and these define what are called open sets. Okay, and the terminology is a bit confusing because open sets refer to something in topology, but open sets are not necessarily open intervals when you think about them on real numbers, because as we saw, if you take a closed interval 0, 1 as the space on X, then the open sets which give a topology to 0, 1 include some things like left closed and right closed intervals and their unions. Okay, so 0, A and things like B, 1. Okay. So this is what topological space is about. There's no notion of distance on a topological space. There's only this notion of neighborhoods, okay, or things belonging to open sets. Now we're going to take, so mathematicians, as I told you, like to think of things in different levels of abstraction, okay. Usually when we think about space, usual space, right, we're thinking in terms of what is called a metric space. So we're slowly going to build up towards that metric space where there's a notion of distance. For the moment, what we're going to do is we're going to go one step beyond a topological space towards the idea of what are called manifolds. Okay, and manifolds take this topological space and they add something to it. They add new features to it, and this feature that you can add is you can do calculus on this manifold. Okay, so the same calculus that you developed on real numbers or complex numbers can now be done on manifolds. Okay, which means that on these spaces, okay, these are now abstract spaces. Okay, they don't have to be real numbers in m dimensions. These are some abstract topological space. In some sense, if those spaces look like Rn, okay, at least locally, if not everywhere, then you can do calculus. You can do the standard differentiation, integration. You can define vectors and tensors. Okay, so we'll see how to do all this. Okay, and basically when we add this extra structure to a topological space, it becomes a manifold. This manifold still doesn't have a notion of distance between different points in the topological space. Okay. But you can do calculus on this. Okay, you can do integrations and differentiations. Okay, so we'll see how to do this. That's the plan for discussing manifolds. And finally, once we're done with discussing manifolds, which will take us a few sessions, then we'll talk about metric spaces where you actually have a metric or a notion of distance between 2 points. Okay, and in general relativity, the idea of a manifold is very important because we are trying to solve for the metric. So the space or space-time doesn't come equipped with a metric. We are trying to figure out what that metric is. So in a sense, we are really describing a manifold in general relativity, which doesn't have a metric. And the solution to Einstein's equation, when you try to find out what the metric is, once you find the metric, then that manifold becomes a particular metric space, which has a metric on it. Okay. So that's why the idea of manifolds is kind of like where we start making the connection with general relativity. Okay, so just as topology was essentially about the idea of these neighborhoods or the continuity of these maps, okay, between topological spaces, maps between manifolds have to do with the with this essential feature of smoothness. Okay, so topology has to do with continuity, and manifolds take this notion of continuity one step further and go to the idea of smoothness of a topological space. Okay. So that's our focus for today is we want to understand what are manifolds. Okay, and there is one simple essential idea to what are manifolds. Okay, the simple essential idea is that we already know how to do calculus on Rn. Okay, this calculus is defined by doing things like taking limit epsilon goes to 0 and then defining that limit through things like epsilons and deltas. Okay. So we already developed a theory of calculus on Rn. Okay. Now what we'd like to do is generalize this calculus to apply to arbitrary topological spaces, okay, except they're not going to be completely arbitrary. These are spaces on which you can potentially borrow the language of calculus on Rn and apply this calculus to these topological spaces. Okay. Um, Now, what do we mean by manifold? Okay, so let me first give you sort of an intuitive definition. So topologically, as a topological space, the manifold satisfies the property that it is locally, okay, homeomorphic, which means that there's a a continuous mapping between a subspace on the manifold and a subspace on Rn, okay, n-dimensional real numbers, okay, for some value of n. And here we assume that when you're talking about Rn, we're thinking about Rn with the usual topology, okay, for Rn. So there's a homeomorphism between manifold, but not over the entire manifold, but at least locally in patches on the manifold. There is a mapping, okay, which is continuous between the manifold and Rn. So roughly speaking, the way to think about a manifold is that we define an n-dimensional manifold as something that looks, okay, looks in quotes, locally like Rn. Okay, we'll try to give a more rigorous definition of what this looks locally like Rn means. Okay, but let's try to get some more intuitive pictures first. So let's go back to this example that we were doing. So supposing you look at an S2, okay, which is the surface of a two-dimensional sphere. Okay, so this is a two-dimensional sphere, meaning the surface is two-dimensional. Okay, so what you can do is this space, okay, is an ideal candidate to be a manifold, because at the moment we're thinking of this as a topological space, okay, but now what you can see is that there are local patches, okay, that is I could take a patch here, okay, and I could take another patch here and so on, and locally these patches, you can map these patches to R2, okay, that is to the real plane, okay, of let's say with, I can think of having an XY ordered pair. Okay, and this local mapping, not over the entire sphere, but locally, okay, within this patch to R2 is a continuous mapping, okay, and it's in fact a homeomorphism. Okay, so so you can define that map, and you can define, let's say, an inverse map, which is also continuous. So you can use this, okay, you can use this mapping to define coordinates on the sphere. Okay, so now this is, you think of this as some abstract space, okay, which has the topology of an S2. What do we mean by topology of an S2? Well, we saw some ways to define the topology of an S2 by thinking of it as embedded in 3 dimensions. Okay, but once you define the topology of an S2, okay, now what you want to do is assign coordinates to, okay, to different points on S2. And the way you can assign coordinates, okay, is one way to do this, okay, is to make a mapping from these patches into R2. Okay, and you can do this in a patch, and you can do this continuously across the patch, okay, which means that roughly speaking, nearby points will have nearby coordinates in R2. Okay, however, what you cannot do, okay, is have a single continuous map which covers the entire two-sphere and maps to R2 in such a way that the map is continuous, or there's a homeomorphism. Okay, and the reason that you can't have such a map is because an S2, the entire S2, is not homeomorphic to R2. Okay, they're in topologically inequivalent spaces. Okay, they're different topologically spaces. In fact, I should say they're inequivalent spaces. Okay, not just that they're different. Different spaces can be considered members of the same class if there's a homeomorphism between them. There is no homeomorphism. There's no continuous map which will deform a two-sphere into a two-dimensional plane. As we already discussed, if I want to make the two-dimensional plane into a two-sphere, I would have to take the point at infinity, okay, and kind of like wrap up the entire plane and map the entire boundary at infinity to a single point. Okay, and that would become the two-sphere. But that is not what R2 is. Okay, so R2 union infinity, okay, if I can define that union in some precise way, that is a two-sphere, but R2 by itself is not a two-sphere. Okay, so there is no continuous map, okay, which means that if I want to put coordinates on S2, I cannot put them in a way that is continuous. I cannot put two-dimensional coordinates. I cannot just put two-dimensional coordinates. That is, I cannot just assign two coordinates A and B, okay, which are real numbers, to every point in S2 in a way that is continuous. Okay. So, for example, let's look at one way in which you could possibly assign coordinates. Okay, so one way in which you can assign coordinates is what you can do is, suppose you have a 2D sphere, you take the North Pole and the South Pole. Now, at the South Pole, you imagine that there's a sheet sitting there. This is an infinite sheet. Okay, sitting at the South Pole. And now I can define an origin of coordinates in this two-dimensional space. This is R2. Okay, so I define this point as 0, 0. And then I define, I have various points on the rail axis. Okay, in, let's say I label them by X and Y coordinates. Now what I can do is I can assign coordinates to a point on a sphere. So let's take this point P. This is an arbitrary point on the sphere. And let's try to assign coordinates to this. So we can uniquely assign coordinates to this by doing what is called a stereographic projection. So the stereographic projection idea is you draw a line. So you imagine this is embedded in 3 dimensions. And now you draw a line from the North Pole through this point. So you draw that line and you continue it till it intersects this infinite sheet. Okay, so it will intersect the infinite sheet here at P prime. So you can do this for any arbitrary point. So if I take some other point here, then I will draw this line, okay, through the North Pole and that other point, and this intersects this point here. Okay, and you can easily convince yourself that for every P, there is a unique P prime in this plane R2. Okay, and therefore I can assign the coordinates of this point P to be the XY coordinates of this point P prime. Okay, so you can do this, and you can do this for almost every point on the sphere, except one. Okay, and that except one is the North Pole itself. Okay, for the North Pole itself, there's no way to define this procedure of drawing a line which is through the North Pole and also the North Pole, because there is an infinite number of such lines. Okay, and those infinite number of such lines are actually run like this. Okay, they are well, okay, sorry. Okay, there's an infinite number of such lines, and if I don't want those lines to overlap with any of these lines, because I don't want to assign the North Pole any of these coordinates, then I would take the natural thing to do is take the limit of this point P as it goes up towards the North Pole, if I want to assign continuous coordinates to the North Pole. So you would imagine drawing, sorry. Yeah, so you'd imagine drawing more and more steep lines like this, and then till eventually you reach this very horizontal line. Okay, that is the limit of the line through the North Pole, except there's an infinite number of such lines because they can be in every direction. Okay, so essentially what you're doing is you're mapping the point at infinity on the rail plane. Okay, you're mapping a point at infinity. Infinity is not a single point, but there are many points. Okay, at infinity, you're mapping them all to the North Pole. Okay, which means that the North Pole has coordinates like infinity, comma anything on x, minus infinity, comma anything on x. Depending on which direction you approach the North Pole, okay, you will get coordinates like this. Okay, so you can see that there is no smooth mapping where in every direction that I approach the North Pole, I will get a unique choice of coordinates for what are the coordinates on the North Pole. Okay, so you can put coordinates on the sphere, two-dimensional coordinates on the sphere almost everywhere except at the North Pole. And the reason is the two-dimensional sphere is not homeomorphic to the two-dimensional rail plane. Okay, that's what prevents you from putting two-dimensional coordinates on the sphere, okay, which are continuous. So the idea is what we would like to do is instead locally, if you take any patch on the sphere, for example, this patch is homeomorphic to R2. Okay, so you imagine an open patch like this. This patch is homeomorphic to R2. So what you would like is choose coordinate patches. Okay, so you can choose a patch like this, and you can assign coordinates on this patch. Okay, there's no problem assigning coordinates on this patch. So let's call this patch U1. We'll assign some coordinates, which we'll call, let's say, x1, x2 on this patch. Then we take another patch like this. This patch could be overlapping with the previous patch. So I've drawn it overlapping here. And this pink region is the region of overlap. Okay, let's call this patch U2. And let's assign coordinates y on this patch. Okay, so the coordinates y are two-dimensional coordinates. So they're y1 and y2. Now, the important point is that the way that we, in this overlap region, okay, the mapping between these two coordinates. These are coordinates which are assigned to the same point. Okay, so I take some point in the overlap region and it has two different coordinates depending on which patch of coordinates you're using. Are you using this patch or this patch? Okay, depending on whichever patch you're using, you'll assign different set of coordinates. Okay, so if you use the U2 patch, you'll assign these coordinates. You use the U1 patch, you'll assign this set of coordinates. You have to make a choice. Okay, but once you make that choice, there should be a way to go from one coordinate system to another coordinate system. Okay, and the essential point is that we demand that going between one coordinate system and another, that should be smooth. What do we mean by smooth? We mean that if I can define these y1 and y2 as functions of x1 and x2. So schematically, I'll write this as y as a function of x, or equivalently, if I think about going from this patch to this patch, I can think about x as a function of y. Okay. These functions, y is a function of x or x is a function of y, where what I really mean by this is something like x1 as a function of y1, y2, x2 as a function of y1, y2. These functions should be infinitely differentiable. That is, I can differentiate them many times and their differentials exist. Okay. If these differentials exist, then I say that these are smooth maps. Okay. So why is it important that a derivative exists? Well, for example, you know that if f of x is, let's say, equal to mod x, right? Then the derivative of this function doesn't exist at x is equal to 0, right? It's infinite, and depending on which direction you approach it, okay. Yeah, okay. So the derivative is infinite. So this is sharp at this point. Okay, it's sharp only in its first derivative. But we don't want it to be sharp in its first derivative, and for simplicity, we'll just assume that it's not sharp in any derivative. Okay, so we'll just assume this simplified criteria of infinitely differentiable. Okay, you don't have to worry about how many times you can differentiate it. As long as you can differentiate it enough times that you can put it in your equations, that's good enough. Okay. Okay. So now basically the idea is that when we have a general manifold, okay, what we'll want to do is we will, so this manifold is a topological space. We will want to take local patches which are homeomorphic to some Rn, okay, and these patches may overlap with each other. And when we join up all these patches, okay, in such a way that we cover the entire space, we have a smooth mapping between this entire space and coordinates Rn, except these coordinates are only defined patchwise. They're not defined over the entire space. Okay. So these patches cover up the manifold and they give us local coordinates. Okay, these coordinates are not valid over the entire manifold. They're only valid in these patches. But in the regions of overlap between patches, you can smoothly transition from one coordinate system to the other. So for example, if I want to go from one region of the manifold to another, I will just hop between coordinate systems as I move along points along this in the manifold like this. Okay, so I'll just hop between points, and there's a smooth mapping from one coordinate system defined in this patch to a different coordinate system on this patch to a different coordinate system on this patch to a different one on this patch. Okay, so the demand that the entire coordinate space can be covered by one single coordinate system, that is something that is not even possible, okay, as you've seen in the case of a two-dimensional sphere. So you cannot make that demand, but what you can demand is that these coordinates patch up in a way that is smooth. Okay, so let me give you another example of a mapping that cannot be done. For example, if you take a circle, okay, and I want to assign coordinates on this circle in a way that is smooth, your standard choice might be to, let's assume the angle theta. Okay, and theta is a natural choice, but again, this is coming from thinking of an embedding of this inside an R2. Okay, imagine embedding this inside a plane. Okay, but again, we don't worry about the embedding. We can assign coordinates theta. Okay, I mean, this is just easy for our visualization because we can easily visualize two-dimensional and three-dimensional spaces. Okay, so now. So now this S1 is a one-dimensional space. Okay, so it's only one-dimensional. So there's only one coordinate, which is theta. Now the question is this theta coordinate valid over the entire circle? So your theta, okay, the first thing that you want is your coordinates are unique. Okay, which means each point should have a unique coordinate. Okay, I shouldn't have confusion about what the coordinate of that point is. So I can't do something like 0, 2 pi because the same point cannot have the label 0 and the label 2 pi. Okay, so one possible choice could be something like this, 0 and 2 pi. Okay, but then you see that the map is not going to be continuous when I'm now thinking of imagining mapping to real numbers. So this is still 2 pi. Okay, now the map is discontinuous as I start approaching 2 pi and I cross over because now it becomes 0. Okay, so the map is not continuous, and the reason it's not continuous is because an S1 is again not homeomorphic to real numbers. Okay, so in order to put a coordinate system on the sphere, you actually on the circle, you need to choose 2 or more patches. Okay, for smoothness. Okay. Okay, any questions here? If this basic idea is clear, then I will move on to the formal definition of what we mean by a manifold. But essentially, it's formalizing this idea of having many coordinate patches which are smoothly connected to each other.
Sir, what will be the 2 patches in this case?
I'll discuss this example specifically once we define the formal definition for manifold. Okay, but let me just give you the quick hint. Okay, so you can do multiple choices. Okay, I can take any point here and any point here and define coordinates on this. Okay, and I can take some point here and some point here. Okay, and take coordinates on this. There's some overlapping region between these patches. Okay, this is one possibility, but there are many other possibilities. In fact, these patches don't even have to be continuous. I can take one patch to be this, 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 and I can take another patch to be this, the union of this, this, and this. Okay, so there's overlap. So this is coordinate system 1. This is these are coordinate system 2. Okay, and it's possible to have maps. Okay, like this also. Okay, the only thing that you cannot do is cover the S1 by a single coordinate, which is continuous over the entire S1. Okay, so your patches themselves can be disconnected. Toshif?
Sir, can you please explain why we, in this case for S1, why can't we have just one patch with R1, mapping with R1?
So I give you an explicit example, right, of this. So let me take 0 to 2 pi, right? This is an example, okay? The problem with this is that the coordinates are not continuous, okay? In the sense that if I go from 0 and I want to sort of, oops. So, okay, let me just tell you intuitively the two demands that we're making on the coordinates, okay? One is that nearby points in the space S1, okay, you can imagine points in the neighborhood, nearby points in S1 have nearby coordinates. Okay, that's roughly the demand for continuity of the coordinates. Okay, the second condition that we're demanding is that each point has a unique coordinate. Okay, both these conditions cannot be simultaneously satisfied for the S1. Okay, and you can see why, right? Because basically, so this condition satisfies this criteria that each point has a unique coordinate. There's no problem there. The problem is that nearby points. So if I take a point which is 2 pi minus epsilon and the point at 0, you see that these points, okay, as epsilon goes to 0, the same in 2 points which are almost in the same neighborhood, right, have very different coordinates. One is at 0 and one is at 2 pi minus epsilon. Okay, so there's a lack of continuity in the coordinate.
Yes, sir, I got it. Sir, and one more thing, like, sir, for that S2, can we also say that S2 is not homeomorphic to R2? Because if we use spherical polar coordinates for theta phi, for the north pole, phi is not defined. This is because...
Yeah, but okay, so that is not an obvious statement, right? So theta phi is one choice of coordinates you can put on the S2. Okay, so this coordinate system doesn't work everywhere on the sphere, as you correctly pointed out. For example, if I take theta is equal to 0, that is the north pole, and it's not, so there's no unique assignment of the north pole to a phi coordinate, right? Do I assign it 0? Do I assign it to 2 pi or pi? Okay, all of these choices in principle work, and there's no unique choice right? And in fact, if you put different choices, the coordinates will not be smooth at the North Pole. Okay, so so this coordinate system doesn't cover the entire sphere. Okay, but this is not a proof that you can't cover the entire sphere. Okay, the proof comes from the fact that these two are not homeomorphic, which requires some work to prove. Okay, but this is essentially showing you the difficulty of trying to put a single coordinate system on the sphere.
Okay, sir.
Okay, any other questions?
Sir, the two conditions that you just wrote above, what exactly do they correspond to?
These two?
Yes, sir.
So this condition has to do with the continuity of the mapping from the manifold M to Rn. Okay, this map is continuous. That is the statement of nearby points in S1 have nearby coordinates. Okay, the second is that the second is obvious, right? That each point has a unique coordinate.
Yes, sir. Sir, actually, my question was like, if these two conditions hold, then what does it signify?
Oh, no. This is just what we would like for in a coordinate system. That's all. It's not
okay.
Yeah, this is what we would like in a coordinate system, right?
Oh, okay.
Okay.
This is how our map should be defined.
This is how a map should be defined, so that intuitively you satisfy these two criteria. The reason is, if you don't satisfy these two criteria, okay, then it becomes a little difficult. So for example, supposing you don't have continuity, okay, of your coordinate system, then you do. It's in a sense you don't have continuity on real numbers, because now you're mapping coordinates to real numbers. And now, for example, supposing I'd assigned, discontinuous coordinates, okay, on this two sphere, for example. So everywhere, like Tosha was saying, suppose I assign theta and phi, but somehow at the North Pole, I arbitrarily assign theta is 0, but I assign phi is 0 also, okay. But phi is equal to 0 is an arbitrary choice. I could, because depending on which direction I'm approaching the North Pole from, okay, I'm approaching with a different value of phi, okay. So now the question is, so something like the derivative with respect to, let's say, so if I arbitrarily assign this map, okay, which is not a continuous map, to the North Pole, okay, then the problem is things like these derivatives, partial theta, partial phi, these will become ill-defined at the North Pole. Okay, since we want the notion of derivatives in calculus, we want to assign smooth coordinates. Okay, that's why we want these smooth coordinates.
Yes, that's clear.
Okay, so now let's come to the formal definition of what we mean by manifold, which is basically whatever I told you is just the exact intuitive idea. All we're going to do is make it mathematically precise. Okay, so the formal definition is we define M, okay, which is a topological space. We imagine M is a topological space, and if M is a topological space, it's also an n-dimensional differentiable manifold if the following conditions are satisfied. One is M is a topological space with some topology T. Okay, we leave this topology unspecified most of the time, so we'll just say it has some topology T. However, M is provided with a family of pairs. Okay, what are these pairs? These pairs are open sets UI. Okay, these are open sets of the topology T. Okay, that is, these open sets UI belong to the topology on this manifold. And these open sets, okay, cover M. Okay, so this is not all the open sets, it's some number of these open sets in such a way that they cover M. Okay, so this is exactly our notion of these patches. Okay, except if you remember that open sets and their unions are also open sets. Okay, so these patches UI can be disconnected from each other. Okay, and the union of all these UI is M. That's what we mean by a covering. Okay, so this covers M. So in other words, UI is an open covering of M, okay, according to the definition that we had given in the last class for what we mean by an open covering. Okay, it's some subcollection of the UIs belonging to the topology T that cover the entire space M. Okay, But this is only the first member of our ordered pair. Okay. The second member is a mapping. Okay. And this is a map. So now you think of these UIs as the patches. Okay. So these UIs are the patch. So this is your manifold. This is a patch. Okay. Which is UI. And now phi I is a homeomorphism. Okay. Which means it's a mapping, a continuous mapping from this patch onto an open subset UI prime of Rn. Okay, so I take Rn, I take an open subset of Rn. What are the open subsets of Rn? As we've discussed, you can think of the open subsets of Rn as open cuboids and their unions, or equivalently, you can think of open balls and their unions. Okay, so this is the standard definition in any GR textbook, is to consider open balls and their unions. Okay, the difference between an open ball and a sphere is the sphere is this collection of points. Okay, so for example, a two sphere is this collection of points. The open ball is sort of a region which is interior to that. Okay, so that is what we call as D2. Okay, it's a a D3. Okay, it's a three-dimensional surface. The surface is a two-dimensional surface. The interior is a three-dimensional surface. Okay. So open balls are homeomorphic to these open cuboids. Okay, so these open balls and their unions define a topology on Rn. Okay, and these define subsets UI prime, open subsets UI prime of Rn. And what we're doing is now we're assigning a mapping from this arbitrary manifold. Okay, and a patch on this arbitrary manifold. We're now assigning a mapping from this patch to some open subset in Rn. Okay. So this is exactly what we mean by assigning coordinates to points in the patch. Okay, so when we give it numbers in Rn, then we're giving it, like, let's say, an x, a y, and that is giving us for every point in this UI, we are now able to assign it coordinates. Okay, and these coordinates are assigned locally. They're not necessarily assigned over the entire M. They're only assigned in this patch. Okay, this patch UI. So now you have to specify not only what is the patch, but you also have to specify the mapping from the patch to Rn. Okay, and then if you can cover the space completely, okay, then you'd say that M is an n-dimensional manifold. Okay, in other words, if M is n-dimensional, you use n coordinates in any patch. Okay. Because this would be a point in Rn. Okay, so in any patch you would assign n coordinates like this to a point in M. Okay. Now, one more important point is the smoothness of the maps in overlapping patches. Okay, so if I have two patches, let's call them UI and UJ. So given a UI and a UJ such that they intersect. Okay, so these are overlapping patches. The map psi ij, okay, which takes you from patch J, sorry, coordinates on patch J to coordinates on patch I. Okay, this function, which takes you from coordinates on one patch to coordinates on another patch in the overlap between the patches, okay, that function is infinitely differentiable. Okay, so that is yeah, so now I think of this. So let me just draw a picture of this. So I've already drawn it here. So here is the white region shows a manifold M, okay, which is some n-dimensional manifold. UI and UJ are two open subsets of M, okay, given some topology on M. Phi I is a mapping from UI to Rn. Okay, so phi I is a mapping from this UI to some Rn. Okay, and in Rn you have some UI prime, which is an open ball or union of open balls in Rn. Okay, so they could be disconnected open balls. Okay, but for simplicity, we'll just assume it. I've just drawn it as connected. Okay, so now you have a mapping from this red region, okay, to this white region, and you can assign coordinates to any point P by finding the point in Rn that it maps to. Okay, and the point that it maps to is denoted as phi I of P. It's phi I is the map that takes you from this UI to UI prime. Okay, so phi I of P should return a a collection of n numbers, okay, x1 to xn. Okay, so this is what we mean by assigning a coordinate to this point P. Similarly, we can do the same thing at uj. We can assign coordinates to any point in uj, and by mapping it to some uj prime in Rn. And the coordinates here, okay, we can label them, let's say, by y. Okay, and now we think of, let's imagine now that we have a point which is in the overlap region, okay, that is in this green region. And let's imagine that in the phi I coordinate system, okay, or in the ui coordinate system, that region, this green region, maps to these points, okay. And let's imagine that in the uj prime coordinate system, that green region maps to these points, okay. Now what we'll do is we will locate the coordinate. So we had some point P in the overlap region. We locate its coordinate in both coordinate systems. Okay, so there's some y1 through yn that corresponds to this point. There's some x1 through xn that corresponds to this point. Okay, and the same point is being labeled in two different coordinate systems. Okay, so depending on which coordinate system you're using, you will use a different labeling for that particular coordinate. The important criteria is that that labeling has to, the maps between these two different labels, that map should be infinitely differentiable. Okay, and since these are both Rn spaces, the notion of functions from Rn to Rn and the differentiability of those functions, that is a well-defined thing that you already know how to deal with. Okay. So now what we do is, so suppose we want to define a point from this point, that is, we're defining a transition from y1 through yn to x1 through xn. So what do we mean? We mean x1 is a function of y1 through yn, x2 is a function of y1 through yn, and so on. Okay, till xn is a function of y1 through yn. And how do we formally define this map? Well, one way to think about it is, so here is the coordinates of the point in uj prime. Okay. So let me call this the coordinates of the point. This point C is C. Let me call this Cj. Okay. So what I will do is from Cj, I will take the inverse map. That is, I will take phi j inverse, which will take me back to this point P. Then I will take the forward map through phi I. Okay, and I will come to this point. Okay. So this is Ci. This is the coordinates in coordinate system I. Okay, which we're calling x coordinates, and these are what we're calling y coordinates. So basically the procedure of going phi j inverse and then doing phi I, which is phi I circle phi j inverse, that is a map which we denote as psi ij, which is a map from y coordinate of the same point to the x coordinate of the same point, where we've just switched coordinate systems in this overlap between the patches. And the claim is that this function psi ij now should be, since this is a function from Rn to Rn, this function is infinitely differentiable in the domain, which is in uj prime. Okay, this function should be infinitely differentiable in uj prime. Okay, so so psi ij, which is defined as this map, phi j inverse, and then you follow this by an operation phi I. So phi I circle phi j inverse. This is taking you from one coordinate system to another. What is the domain? The domain is, you first find the intersection region of ui intersection uj, and then you find the region in uj prime that corresponds to that. Okay, and how do you find that? Phi j gives me the coordinates of this point. So phi j on any point in ui intersection uj, okay, is this region. Okay, so this is the domain of this function. Okay, this is the domain of psi ij. And the range, okay, is going to be this region. Okay, that is the green points map to, so now they're pink, map to this region. Okay, and this region over here is phi I acting on that same region ui intersection uj. Okay, because I acted with this function to get the coordinates of these points. Okay, in the ui coordinate system. So this function psi ij, which goes from this domain phi j ui intersection uj, that is, these are the coordinates of these overlap region in the j coordinate system, to the coordinates in the I coordinate system. This map is is a function from some subspace on Rn to another subspace on Rn, and we know how to define differentiability on Rn. this map is infinitely differentiable. That's what we mean by a smooth transition between overlapping patches. Okay. Okay, so in other words, I just said this here. So if P lies in the overlap region, Ui intersection Uj, this psi ij, this transition function, which takes you from one coordinate system to another in the overlap between these two patches, is a map from some subspace in Rn to another subspace in Rn. Psi ij is infinitely differentiable. Okay, this is a condition that is Rn using epsilon and delta. So we'll assume that the notion of differentiability and all that is something that is well defined on Rn. Okay. Okay. Any questions here about this idea? This is the key picture really to understand. So is this clear or is this too fast? Let me know. Or are you still processing?
So this part is clear.
Okay, what about the others? Toshif, yeah, you have a question?
Sir, does the topological space have to be Hausdorff for this to be manifold?
Does the topological space have to be Hausdorff? No, you can. I think you can define manifolds which are not Hausdorff, but we will generally be working Hausdorff manifolds. So we will assume the property of Hausdorff.
Okay, sir.
Okay. So there are some, there's some weird spaces which are not Hausdorff, and there's another property called paracompactness. We only define compactness. If a space doesn't satisfy these properties, you can still define a manifold in the sense that you can still define calculus on it, but there are some other problems that arise. Like you can't define a metric on some of these spaces. Yeah. Any other questions? Okay, so let's go ahead. Okay, so now that we formalize this notion, okay, let's just recap those properties. Okay, so if you want M to be a manifold, it must have the following things. One is it must be a topological space with some topology T. The second thing is that it should come with a family of pairs. Okay, so it should come with a family of pairs, UIs, which cover the entire space. So UI is some open covering of phi of M, and it should come with a bunch of maps from those UIs to open sets in Rn. Okay, and these maps should be homeomorphisms. Okay, so that means roughly what you're saying is that M is locally looks like Rn. Okay, so we are formalizing that by saying that open sets in M map to can be homeomorphically mapped to open sets in Rn. Okay, but this doesn't mean that the entire M is homeomorphic to Rn. It only means some regions of M are homeomorphic to Rn. Just like on the two sphere, certain regions are homeomorphic to R2, but not the entire two sphere. Okay. So you're defining a notion of UIs, which are patches, and for each patch you have a map, okay, to Rn, which assigns coordinates. Okay, so this is assigning coordinates to the patch. And the most important thing, okay, about these manifolds is that in the overlap region between two patches, the maps, now I can think about I mean, either I could have thought about, this complicated way of going from the coordinates back to the point and then back to a new set of coordinates in the overlap region, or I can directly think about the transition from one coordinate system to another. That transition from one coordinate system to another has to be infinitely differentiable. That's what we mean by a smooth manifold. Okay, so this is the criteria for smoothness. Okay, so just like we saw that topological spaces, okay, even though the idea, the definition was very simple, it was quite rich, okay, in the sense of you can have many different kinds of topological spaces with that definition. Similarly, there can be many manifolds, okay, with this definition. And there are lots of deep consequences, okay, just arising from this definition, okay. So a couple of things to just keep in mind. One is, so I'll just talk about some things in no particular order. So first is that the manifold is an abstract topological space. Okay, so you don't think of, let's say, a two-sphere as being embedded in 3 dimensions. The two-sphere exists on its own. Okay, a circle exists on its own. Okay, this is the notion of an abstract topological space on which you're trying to assign coordinates. Okay, the spaces can be much more complicated, and you're trying to assign coordinates to those abstract spaces. Now, the space itself does not necessarily come with coordinates on it. Okay, you can choose coordinates on it, but the space itself you should think of as an abstraction. It's a collection of points, okay, with a certain topology. So you can assign coordinates by mapping open sets on this space, okay, or in patches to Rn, but we don't think of the coordinates themselves as directly being the points on M. Okay, so this is a slight difference in viewpoint. Normally, when you think about, you don't worry about this distinction at all, right? When you're thinking about, let's say, usual space, right? You say, okay, I just pick an origin, and then that point is 3, 0. Okay, but that point is not 3, 0. You're assigning it coordinates 3, 0. Okay, and but that point is just a point. Okay, in the physical space that we live in. Okay, similarly, these topological spaces are abstract spaces, and the points are just points, and we are assigning them coordinates. Okay, so the points exist independently of their coordinates, or whether or not you've assigned them coordinates. The points themselves exist in that topological space. Okay. The second thing is that these pairs, the patches and their maps from the patch to Rn, this patch is called a chart. Okay, or in mathematicians call it a chart. Physicists would call it a local coordinate system. Local because it doesn't necessarily cover the entire space. It only covers a region of that space, of that topological space. Okay, now this whole family, okay, of charts, okay, that is patches and maps to Rn. Okay, so if I imagine this is a two-sphere and I imagine various patches, okay, one place that you would have seen this, right, is an atlas, right? Because in an atlas, if you take the map of the Earth, you would break it up into, let's say, North America, South America, different continents. Okay, and each patch would have overlaps with other patches. Like the map of Asia will have some parts of Europe, right, and so on. Okay, so this would be overlapping regions. And this whole family, okay, of charts similarly on this abstract topological space is also called an atlas. Okay, so the entire collection of charts, that is the patches and the maps to coordinates in Rn. Okay, this collection together of these ordered pairs is called an atlas. Okay, so each of these patches individually you can think of as a map inside an atlas. Okay, or a chart. And UI, okay, is called the coordinate neighborhood. Okay, it's called a coordinate neighborhood. And phi I is what we call a coordinate function, or in short, we call it the coordinate. Okay, phi I of some p gives me the coordinates of that p in the patch UI. Okay. And what is phi I? Phi I is a mapping from an open set in M. Okay, this belongs to M, to an open set UI prime, which is open balls or unions of open balls in Rn. Okay, it's a homeomorphism between them. It's a continuous map between them. And these can be represented as n functions. Okay, that is, if I have a point P which belongs to this UI, which is a subset of M, okay, then I can represent the coordinates of this by n functions, x1 of P, x2 of P, xn of P. But these are not functions in the sense of real numbers to real numbers. These are functions from points in an abstract topological space to Rn. So you can't do calculus on these functions. Okay, you can't do calculus on these functions. There is no way to do calculus on these functions because we don't know how to define differentiation on these arbitrary manifolds. What we do know how to do is differentiation if you have from Rn to Rn. Okay, this is why the notion of overlapping coordinate patches is very important. Okay, so here P belongs to these UIs, and these x1, x2, xn, they belong to Rn. Okay, so this function, these coordinates take me from a point in this abstract space and they bring me to Rn. Rn is something concrete that I know how to deal with. Okay, so sometimes when there's no confusion about which patch we're talking about, okay, we'll use this sloppy notation. Okay, this is very common, and especially physicists tend to be very sloppy with the notation. But it's more convenient to just write x1 through xn and say that these are the coordinates. But what we really mean is we have to be careful about which patch we're talking about. Okay, because in different patches you'll assign different. There's a different coordinate system. So to denote a point with these coordinates, if there's only, let's say, one coordinate system in use, typically we'll just write x1 through xn. Okay. The other thing is the existence of this local homeomorphism. Okay, so this local homeomorphism, let's say from an S2, some region looks locally like some open region in in R2. Okay, so locally the two sphere looks like R2, but not globally. The entire S2 is not homeomorphic to R2. Okay, as we've discussed, you need to take R2 union infinity, which is not the same as R2. Okay. Okay. And now, if we now take a point P in some overlap region between two of these patches, then we can define maps phi I, which take this point to one set of coordinates, which we'll denote as x mu. Okay, mu goes from 1 through n. Okay, because there are n coordinates that you assign. And in another region in uj, okay, so depending on which coordinate system you're using, and you can use either coordinate system in the intersection region, phi j will assign, the map phi j will assign some coordinates, we'll denote them as y, okay, and we'll denote them as y nu, where nu goes from 1 through n, okay, where this x belongs to some Rn, and more specifically it belongs to some open subset of Rn, and y also belongs to some open subset of Rn. And these are two different coordinates which are assigned to exactly the same point, okay, but in different patches. And this transition function psi ij, okay, which is a map from one coordinate system, that is the j coordinate system, to the I coordinate system, okay. In shorthand, we can write that transformation as x as a function of y. Okay, what we really mean is let's go back from y to the point P, then from P let's go to the point x. Okay, that is, we'll go from the coordinates in one coordinate system to the coordinates in another coordinate system. Okay, so this is a transition from y coordinates to x coordinates, and in shorthand we can denote it as x as a function of y, where this is real numbers in Rn. Okay, in the domain is Rn, which is the y coordinate, and the range is the in Rn. Sorry, not the range. Strictly speaking, this y belongs to the subset, open subset, ui prime, sorry, uj prime, and this x coordinate belongs to ui prime. Okay, so this is, and these are subsets of Rn. So these are maps from one subset of Rn to another subset of Rn. These transition functions x of y are infinitely differentiable, or equivalently y of x. So if I do psi ij, this is a map from y to x, and this map is C infinity. Okay, so what do we mean by this map being C infinity? That is, what do we mean by this x of y being infinitely differentiable? That means that you can take derivatives like this for any of these x coordinates. Okay, so let me take x0 for example. Okay, I'll label the coordinates by 1 to n minus 1, let's say. So if I take x0 and then I differentiate with respect to any y, okay, so let's say I differentiate with respect to y1, I differentiate with respect to y3, and I differentiate with respect to y5. And I differentiate with respect to y1 10 times, I differentiate with respect to y3 7 times, differentiate with respect to y5 12 times. This derivative is well defined and it exists. And it doesn't matter how many of these y's I differentiate with respect to, and it doesn't matter how many times I differentiate. Okay, each of those x's can be differentiated as many times as you want. Okay, that's what we mean by infinitely differentiable. In shorthand, infinitely differentiable is denoted by the symbol C infinity functions. Okay, these functions are said to be C infinity functions. Okay. Okay. I'll just pause here again for more questions. Okay. Okay. So now let's suppose that you have on the same topological space M. Okay. You can put two different atlases. That is, you imagine that this is the topological space and this is the topological space, but let's imagine that we cover it with a different collection of charts. Okay, so one collection of charts is like this, but let's say the other collection of charts is something like this. Okay, so this covers the entire space. So one atlas, okay, which describes all these charts is A1, and another atlas which describes all these charts on the same topological space is A2. Okay. Now, if these atlases A1 and A2 are such that if I take their union, okay, and the union is also an atlas, okay, how could that be an atlas? Well, you can see one thing easily, right? So if I take this, okay, this is in one atlas, and now I take the charts of this other atlas, that is, I take this chart, okay, which is this region, and I take this chart, which is this region, and I take this chart, which is this region. Okay, the union of them can also be an atlas, right? I mean, there's a redundancy of extra overlaps, but that's okay. There's no constraint on how much overlap you can have, okay, when you define a manifold. So if when you take the union also, these you still get an atlas, then you say that A1 and A2 are compatible atlases. Okay, you should say that both these atlases are compatible with each other. Okay, that is, you can take the union and still get an atlas. Okay, it's not obvious that you will always get an atlas. Okay, but most typical examples that you would think of, it seems obvious that it should happen. Okay, I mean, it seems obvious that it should happen. It's not really obvious that it does. Okay, if you try to prove it, because what it requires is that when I take these other atlases and now I take, let's say, a chart V. Okay, so let's say in atlas 2, these charts are denoted as Vi, phi I, or Vj, phi j. What I need to do now is ensure that my old charts Ui, phi I, and my new charts Vj, phi j. Okay, certainly the UIs and VIs together will cover the entire space, right? Because the U's individually cover the entire space, V's individually cover the entire space. The non-obvious thing is to ensure that the maps between these two coordinate systems, in the overlap region. So if I take the overlap region of any of these new charts with the old charts, okay. So let's say if I pick this chart here and I pick this new chart here, the overlap region is here. Okay, and in that new overlap region, these are new overlap regions which are created by the union of these two atlases. In those new overlap regions, what I want is that these functions, which now take me from one atlas to another atlas, that these are also infinitely differentiable. Okay, it's not obvious that this is always going to be true, that the union of these two atlases will also be infinitely differentiable. Most cases that we will consider, it will be true, okay, that these atlases will be compatible. This idea of compatibility, okay, between atlases, that is, I can take two different atlases and they're equivalent to each other. This actually gives us what is called an equivalence relation on manifolds. Okay, and you'd say that manifold M with an atlas A belongs to an equivalence class. Okay, and they are said to have the same differentiable structure. Okay, that is, you say that a manifold M with an atlas A is related A1 is related to a manifold M with an atlas A2, okay, if the atlases are compatible. That is, if you say that these two are related, if this is also a manifold. Okay, a manifold with a valid atlas. Okay, so now you can see that this, you can check that this condition defines an equivalence relation in the sense of equivalence relations that we defined in the last class. So just like you had this equivalence relation of homeomorphisms between topological spaces, this is now an equivalence relationship between manifolds. Okay, so manifolds which have the same, which belong, so now this equivalence relation partitions the space of manifolds into classes. Okay, so all members of one class will have charts such that you can unionize them. That is, you can group these atlases together, and you'll still get a new, you'll get an atlas. Okay, so all of one type. Okay, this will be one class. All of another type, okay, will be another class. Then one. Sorry, it's the same topological space M. Sorry, everywhere it's the same topological space M. Okay, it's just different atlases on this topological space. So it's M, A1 prime, M, A2 prime, and so on. But I can't combine a member from this class with this class. The atlases are incompatible with each other. That is, if I try to take the union of A1 and A1 prime, that does not give me a valid atlas, okay, on M, because maybe those functions are discontinuous, okay, at some order in derivatives. So this entire class, okay, the manifolds in this entire class with these different choices of atlases, they are said to have the same differentiable structure. Okay, the same differentiable structure. Okay, so yeah, so like I said, you can imagine one collection of charts that looks like this, and another collection of charts that, let's say, is you cover the two sphere with only two charts, this pink region and the green region. Okay, let's say like the upper hemisphere and lower hemisphere with a slight overlap. And these two charts actually fall into the same equivalence class. Okay, they're members of the same equivalence class, and they have the same differentiable structure. Okay, that is, if you take the union of these atlases, you still get another atlas. So the surprising thing about this differentiable structure is it's not unique. Okay, that is, there's not just one equivalence class. Sometimes there can be multiple equivalence classes which are incompatible with each other. However, these examples, the known examples only exist in, let's say, higher dimensions, let's say on an 7-dimensional sphere. So we won't worry about these kind of cases. Okay, for our purposes, we will assume a unique differentiable structure. That is, there's only one equivalence class for each manifold. So it doesn't matter whether you choose one atlas or another atlas. Okay, all these atlases are compatible. So I could take the union of my atlas with your atlas, and we'd still get another atlas which works perfectly well on the manifold, which means that even if I chose a different set of patches and you chose a different set of patches, we can always take the union of our choices of patches and get a valid coordinate system. And then I know how to translate my coordinates into your coordinates, okay, by going from one patch on my coordinate system to one patch in your coordinate system. Okay, so so basically, it's not important if the differentiable structure is unique. That is, there's only one equivalence class. It doesn't matter which patches you choose. Okay, as long as you find some set of patches on which you can find a coordinate system, then all our choices are equivalent. Okay, or at least we can make them equivalent. Okay, by taking your patches, my patches, putting them together and finding transition functions between them. Okay. So these are okay. So now let's finally do some examples. Okay, to understand this. So the simplest example is, let's say your manifold M is the topological space Rm. Okay, with the usual topology. And now this Rm is already topologically identical to Rm, okay, which means that I can cover the entire manifold by a single chart. Okay, so I can use a single chart that covers the whole space. Okay, because as we've seen before, if X is a topological space, then X itself belongs to T. Okay, T contains both the null set and X. So X itself is a valid open subset, okay, which means that the entire space Rm is a valid open subset of Rm. And phi, I can just choose phi to be like, let's say, an identity map. Okay, so if I have some point in Rm, I choose the same point in Rm. Okay, and I choose the identity map. This is typically what we mean when we think about Euclidean space. Okay, so if we think about Euclidean space, let's say if we imagine the world as Euclidean, which till now we always imagined it was, right, before the general theory of relativity. So you have X, Y, and Z, and then you basically say that okay, points in the real world are an abstract space or physical space. They're not coordinates, but now I can assign coordinates to them by mapping them to Rn, okay, to points in Rn. And you can do this covering with a single chart. Okay, so this was never a problem before. Okay, because our space was homeomorphic to Rm. The entire space is homeomorphic to, in particular, R3. Okay, entire space is homeomorphic to R3. But it's not obvious that space is R3, right? So maybe you can't cover the entire space by a single set of coordinates. Okay, so in that case, that's why you want to be more general and talk about different choices of these coordinate patches which cover your topological space. So now let's come back to that example that we were doing earlier. Let's imagine that we take an S1. Okay, we take a circle, and we want to assign these coordinates on the circle. Okay, so one thing that we can do is we can't assign coordinates everywhere in the circle smoothly, but what we can do is we can exclude one point at a time. So in the first case, we'll exclude this point. Okay, and in the second case, we'll exclude this point. So the first patch is, roughly speaking, the first coordinate patch is an open set which goes from here to here and excluding this point. The second patch is an open set that goes from here to here and excluding this point. So the first patch is the entire S1 minus this point P. Okay, and the second patch is the entire S1 minus this point P prime. Okay, that's over here. So these are my two patches. Okay, and now what is the mapping from this patch to real numbers? So what I can do is, once again, I can define, let's say, phi 1, okay, as the mapping from this patch, okay, which is now defined as the entire S1 minus this point. I can denote it by a number theta. Okay, and theta is, let's say, in the usual way of thinking about the embedding in R2, theta describes the angle of this point made with the x-axis. Okay, and now this theta coordinate, okay, belongs to the open interval 0 to 2 pi. Okay, note that the point 0 is not included, so we've excluded this point from our patch. Okay, so theta belongs to the open interval 0 to 2 pi. This is one choice of coordinates that I made. This is by no means the only choice. This is one possible choice I could have made for this set. Okay, so I made this choice. Okay, I could have also chosen, let's say, and since 0 to 2 pi is isomorphic, I could have chosen 0 to 1. Okay, I could have chosen 0 to, or more conventionally, I could have also chosen something like 2 pi to 4 pi. Okay, but I could have also equally well chosen 0 to 1. Those are also perfectly valid coordinate choices. Okay, so what do I mean by 0 to 1? Let's say in some smooth way, okay, some continuous way, I map the point 0, something like epsilon over here, okay, where epsilon is some number slightly greater than 0, and I go on increasing epsilon, increasing the coordinate till I come to this point, and I assign this point the coordinate something which is very close to 1, so something like 1 minus some epsilon, right? Okay, so I can sort of stretch the coordinate. I'm free to do that, right? Nobody decides what coordinate I get to choose. I can choose any coordinate that I like. So the 0 to 2 pi is one choice, okay? And that notion of 0 to 2 pi comes from thinking about the embedding in R2. But you're free to choose any other coordinate that you want, okay? You're perfectly free to do that. This entire space that we chose, okay, is isomorphic to an open line segment, okay? So the entire space that we chose, if we remove this point from S1, the space that we chose is isomorphic to an open line segment, which means if the map to a subspace of R is homeomorphic, we can map to open subspaces which are homeomorphic to open line segments, which means we can choose any open line segment on R. Okay, this is an open ball in R, okay, is in one dimension. And therefore any open interval, okay, on R, would give me a valid choice of coordinates, okay, on a valid range of coordinates for this this domain, this U1, which is S1 minus P. Okay, so this is a very important thing that you need to understand, is that this is by no means the only choice of coordinates, 0 to 2 pi. You're free to make any choice of coordinates as long as you choose an appropriately homeomorphic region in R, in this case an open line segment. Okay, all right. Now we can do the same thing for our second coordinate patch. Okay, so let's just remember what our second coordinate patch is. Our second coordinate patch is the entire circle minus P prime. Okay, which means that we can go like this. Okay, so this will now we'll assign a coordinate theta prime. Okay, and again theta prime, just for simplicity, based on our intuition, we will map it to an angle, except the angle we will not take it to be between 0 and 2 pi. We will take the angle to be between minus pi and pi. Okay, this is for obvious reasons. When you're excluding this point, okay, the point, whether is this point pi or is this point minus pi, okay, that confusion is irrelevant if I choose the range minus pi to pi. Okay, so that is, this point is 0, this point is something slightly less than pi, and if I come this way, then this point is something less, slightly larger than minus pi. Okay, and I don't have to have continuity this way because this point has been excluded, okay, from my patch. Okay, so this is another choice, but again, this minus pi to pi is not by no means sacred. We could have chosen any other choice of coordinates. We could have again chosen 0 to 1, minus 1 to 5. Okay, whatever we like. Okay, as the coordinate system. So, but let's just go with these canonical choices. Okay, there's nothing wrong with these canonical choices. Okay, so we can choose these canonical choices. Now, the first thing is, okay, the phi1 inverse and phi2 inverse exist. Okay, that means if you tell me which patch you are in, so if you tell me you're in the patch U1, and you tell me the coordinate value, that is, you tell me theta, then I can tell you which point on the circle you're talking about. Okay, that is, I can go back from the coordinate to the point. Okay, so these inverses exist. Okay, by construction, because we've assigned unique coordinates to each point. Okay, that is, this map is 1-to-1 in this patch. Okay, so we do a 1-to-1 map in this patch. Okay, and these functions, okay, phi1, phi2, phi1 inverse, phi2 inverse, these are continuous functions. Okay, and these maps phi1 and phi2 are homeomorphisms. Okay, they're homeomorphisms from phi1 to an open set, which is an open ball in Rn. Okay, the important point is that the topology of this open set U1 is identical to the topology of this open set in Rn. Okay, for simplicity, we're just taking a region which is an open interval or an open ball. Okay, so these maps are homeomorphisms. Okay, these continuous maps are homeomorphisms. Now what we want to do is we want to look at some point, okay, in the overlap region between these two patches. Okay, so some point like this. Okay, and in each patch we will assign this point different coordinates. Okay, so for example, and now what we want to do, right, is we want to define, as I change coordinate, so I can either label this by a theta coordinate or I can label it by a theta prime coordinate. Theta corresponds to using the coordinate of the first patch. Theta prime corresponds to using the coordinate of the second patch. Okay. Now what we would like to do is define functions, okay, from one coordinate system, okay, let's say the second coordinate system to the first coordinate system. That is, these are functions from theta prime to theta. Okay, and in shorthand, I write them as theta is a function of theta prime. Or equivalently, or alternatively, I can have mappings from theta to theta prime. That is, I can go from this coordinate system, the U1 coordinate system, to the U2 coordinate system. Okay, again, this is only valid in the overlap region. Okay, this is not valid in regions where these coordinate systems do not overlap. And the important point is that my coordinates have to be chosen in such a way, okay, and this we have to check now, is in such a way that these functions, these transition functions between different coordinate systems are smooth in the overlap regions of those patches. Okay. So when we say that these functions are smooth, so let's be clear. So the overlap region is the intersection of those two. The intersection of these two things that I've drawn. Okay, so the intersection of this, which is S1 minus this point P, and S1 minus the point P prime, which is the red circle with that hole over here. Okay, so what is the overlap of these two patches? Well, the overlap is basically you exclude both these points, okay, because this patch is only part of one coordinate system. This point is part of only one coordinate system, and this point is only part of one patch. Okay, so you exclude both these points, and what this does then is it splits the circle into two disconnected regions. Okay, so the overlap region between those two patches, U1 and U2, is now split into disconnected regions. It's the top region and a bottom region. Okay, the top of the circle and the bottom of the circle. And in the top of the circle, so in one coordinate system, we're using coordinates between 0 and 2 pi. In the other coordinate system, the one coordinate system, we're using this. In this two coordinate system, we're using the coordinates minus pi to pi. Okay, so in the top coordinate system, the coordinates actually agree. Okay, which means that if I take a theta value here, this value lies between 0 to pi. And in the theta prime coordinate system, also that value will lie between 0 to pi. Okay, and so the map between these coordinates is very simple. In the top region, theta of theta prime is just theta prime. Okay, that is theta is equal to theta prime. Okay, in the top region. In the bottom region, however, they differ. Okay, in the bottom region, the coordinates using the one coordinate system go from something like pi to 2 pi. Okay, except we're excluding the point pi and 2 pi in the overlap region. In the two coordinate system, these coordinates go from minus pi from here to pi over here. Okay, so in the two coordinate system, if I want to relate it to the coordinate in the one coordinate system, what I have to do is I have to add 2 pi. Okay, to my coordinate value. So theta of theta prime is not just theta prime, but it's now theta prime plus 2 pi. Okay, so in the bottom part of this patch or of the overlap region, this is what we have. Okay, but here's the amazing thing. This entire function, okay, is infinitely differentiable on its domain. Okay, on its domain, it is infinitely differentiable. What is the domain? The domain is this open region union this open region. Actually, strictly speaking, it's not these regions. These regions are on the manifold. The map is to coordinates, which are coordinates between minus pi to pi, okay, which is an interval on the rail line. So that is the domain of theta prime. Okay, and now we've by excluding the overlap region, we've actually split this into 0 to pi union minus pi to 0. Okay, so from this domain to the range 0 pi pi comma 2 pi, okay, union pi comma 2 pi, you've defined functions theta prime to theta, okay, on this domain, which go to this range. Okay, and these functions are infinitely differentiable. Okay, this doesn't look smooth, but you see that in each of these broken neighborhoods, it's a perfectly smooth, infinitely differentiable function. I differentiate it once, I get 1. I differentiate it twice, I get 0, and so on. In this region, if I differentiate it, I get 1, I get 0, and so on. The functions are different in different regions. Okay, but the differential is well defined. Okay, the differential is well defined, and in fact, to define differentiation on the lower region, I never have to refer to the top region, because any neighborhood of some point in this region is always some point over here. Okay, or in other words, if I look at the 0 to pi range, any epsilon delta neighborhood of some point here always lies in one of these disconnected regions. If I choose a point in this region, an epsilon delta neighborhood of that lies here. So all the derivatives become well defined, because all the derivatives are only restricted to this region, right? To function values between this region. Okay, and similarly, the domains are restricted to these separately broken regions. So this entire function over these split up domain, this disconnected domain, is actually infinitely differentiable. So this is an infinitely differentiable function on the domain which is T and B, okay, the top and the bottom. And similarly, you can just you can invert this map and get theta prime as a function of theta, okay, and that is also infinitely differentiable, okay, and that's easy to see what the inverse of this function is. Okay, sorry, this is theta is equal to theta prime plus 2 pi. Okay, any questions about this example?
Sir, can you explain once more the thing that you wrote on the left, this box?
This one?
Yes, sir, that one.
Okay, so so when I say that this is the function, okay, so let me just make this clear. Okay, so this is my manifold, which is the circle. Okay, this is my coordinate system 1. Okay, so let me call this U1. Okay, this is my patch U1, sorry, not my coordinate system. And now let me draw another patch which excludes this point, which I'll draw like this. This is U2. Okay. Now to U1, I assign coordinates, and these coordinates are assigned between 0 to 2 pi, okay, which is an open interval, an open subset in R. On U2, I assign the coordinates minus pi to pi. Okay. Now the overlap region, that is U1 intersection U2, as we already discussed, is this disconnected top and bottom, okay, where we exclude both those points. Now, when we look at the coordinates of the top and bottom regions in the U1 coordinate system, okay, then what we are doing is essentially we're breaking the 0 to 2 pi, okay, because this point was actually this point was included in the U1 coordinate system, but we exclude it when we look at the overlap region. Okay, so when we look at the overlap region, that is, we're looking at the coordinates phi1 of this U1 U2 region. Those coordinates don't cover the entire 0 to 2 pi, rather they cover only the range 0 to pi union open interval pi to 2 pi. That is, they exclude this point. Okay. Similarly, when I take U2, now this point was actually included in U2, but when I take the overlap region, I exclude that point. And what that does is, now when I take the coordinates of U2, of any point in U2 in the overlap region, then what it does is it assigns a coordinate, but the coordinates don't cover the entire minus pi to pi. They now cover minus pi to 0 union 0 to pi. Okay, so this coordinate is what we call theta. This coordinate is this coordinate is what we call theta prime. This coordinate is what we call theta. Oops. Okay. Now what we're looking at is, when we look at transition functions, we have to look at transition functions which are restricted to the overlap region, okay, or the coordinates on the overlap region. So on the overlap region, I look at theta, okay, and theta lies in this domain. And in the overlap region, I look at theta prime. And the functions from theta to theta prime or theta prime to theta, they should be infinitely differentiable only on this domain. They don't need to be differentiable over the entire circle, only in the overlap. Okay, which is why when you look at this function, theta is equal to theta prime and theta is equal to theta prime plus 2 pi, this apparent discontinuity okay, in the definition is not a lack of smoothness. Okay, this is still infinitely differentiable because the top region and the bottom region, okay, this is the top region. I mean, these are the coordinates of the top region. These are the coordinates of the bottom region in coordinate system 2. These are the coordinates of the top region, and these are the coordinates of the top region. These are the coordinates of the bottom region in system 1. Separately in the top region, these coordinates are differentiable. Separately in the bottom region, these coordinates are differentiable. The issue of differentiation in transitioning from the top to the bottom never arises because these are disconnected regions. Okay, so so any point in this, so what do you mean by a differentiation? When you say f of x is equal to, f prime of x is f of x plus epsilon minus f of x divided by epsilon in the limit epsilon goes to 0. Okay, you're looking at a point which is in an epsilon neighborhood of x, but all epsilon neighborhoods of x, okay, if you choose a point x in this range, all epsilon neighborhoods of x lie only here. If you choose an x in this region, all epsilon neighborhoods of x lie only here. Okay, so the issue of overlaps of these two regions when taking derivatives never arises.
Yes, sir. Sir, I got it. Sir, when you first wrote it, seemed like you included minus by, like that's why I asked. Like these are open intervals.
These are, sorry, these are all open intervals.
Yeah, that's why I asked.
Okay. Okay, so I'll just do one last example and then we'll stop. Okay. So the last example is that we'll take Sn, okay, and we'll realize them in Rn plus 1. Okay, so again, Sn itself is an n-dimensional sphere, which you can think of as having its own topology. But it's easiest to think of the topology inherited, okay, or induced by its embedding in Rn plus 1. So as we've seen before, the equation which defines it in Rn plus 1 is, you define it like this, okay, xi square, where so in n plus 1 dimensions, you have n plus 1 xi values. Their square sum is equal to 1. That defines an n-dimensional surface, which is Sn. Okay, so for example, in 2 dimensions, x1 square plus x2 square is equal to 1 defines a unit circle. In 3 dimensions, x1 square plus x2 square plus x3 square is equal to 1. So this defines a circle. This defines a 2-sphere. Okay, this defines a 2-sphere. So now here's the important thing. Okay, this is embedded in n plus 1 dimensions. But you can't use, okay, with the definitions that we are following, you can't use x1 through xn plus 1 as the coordinates on this sphere. Okay, why not? Because for this sphere is, let's say, for example, a 2-dimensional surface. Okay, or this circle was a 2-dimensional, a circle was a 1-dimensional surface. So why can't I assign 2 coordinates? For example, a point on a circle, why can't I assign both an x coordinate and say x is equal to r cos theta, y is equal to r sine theta, but I just fix the value of r to be 1. Okay, you could do this, but really what you're doing is okay, but I don't want to think of the coordinates as x and y. Okay, I want to think of the coordinate as theta. Okay, and theta itself is problematic because that cannot cover the entire space. Now, why is it that we don't want to consider the coordinates x and y? Okay, the reason we don't want to consider the coordinates x and y is a circle is only a 1-dimensional object. It's embedded inside 2 dimensions, which means you can certainly in 2 dimensions you can define derivatives with respect to x and derivatives with respect to y. Okay, but the problem arises when you want to define calculus which is on the circle itself. Okay, when you want to define calculus on the circle itself, you want to be able to define some notion of a derivative with respect to theta, that is motion in as I change the coordinate, how to take derivatives. Okay, and that is not going, this partial theta is not going to be well defined in terms of x's and y's. Okay, I need to assign coordinates intrinsically on this 1-dimensional space. Okay, so the embedding of a manifold inside another manifold is not a good way to assign coordinates. Another way to see how this is incorporated into the definition is S1 embedded in R2 is not an open subset of R2. Okay, it's a closed subset of R2. It's a closed subset in the topological sense. Okay, so for example, points in R2 which are just around S1, okay, which exist in open balls around S1, those are not part of the neighborhood of this S1. So any point outside the circle is not part, even though it's very close to the circle, is not part of the circle. Okay, which means that the mapping that I'm doing now from this open, so if I assign coordinates on R2, I would assign this, map this to an R2. And that mapping is not going to be smooth, okay, because the circle itself is not homeomorphic to a patch in R2. It's homeomorphic to a patch in R1. Okay, so that's why essentially you're running into this problem. Okay, which is why we really don't want to think about coordinates in an embedding, okay, of the manifold. What we really want to think about is somehow assign coordinates on the space itself without any reference to any kind of embedding. Okay, because this will not help you to do calculus on the manifold. Okay, so intuitively we want to define a notion of smoothness on the sphere without reference to any kind of embedding in n dimensions. Okay, so let me give you an example of one coordinate system that you can use. Okay, and then you can try to work out some of these details for yourself. Okay, I'll put up the notes so that the notes are up, so anyway you can see them. So what you can do is you can define 2 times n plus 1 patches. Okay, so let's see how to do this. So as we said, any point can be, you can reference it by its n plus 1 coordinates. Okay, in n plus 1 dimensions, but this is not going to be a smooth mapping. But what you can do is you can now take patches on this n dimensional sphere. So for example, you can take a patch where, let's say, one of these coordinates, let's say the xi coordinate is positive. Okay, so you don't consider the regions where it's 0 or negative. That defines a patch. So for example, on a 2-dimensional sphere, which is in x, y, and z, okay, you're taking the upper hemisphere. Okay, that is, you're considering the regions where z is greater than 0. Okay, that is one patch. Okay, that is xi is greater than 0. Some xi. And for every such choice of xi, you can define one patch, and you can define another patch, which is the lower hemisphere. Okay, which is the lower hemisphere. So again, you can assign coordinates, but these coordinates are not the good coordinates that we want, because these coordinates are in n plus 1 dimensions. Now, however, what we can do is we can go from this n plus 1 dimensional coordinates to n dimensional coordinates by simply dropping for each upper hemisphere and lower hemisphere, we simply drop the z coordinate. Okay. In other words, what we're doing is for this 2-dimensional sphere, when you drop the z coordinate, you're taking this point and just mapping it to a point in the xy plane. Okay. This mapping is unique as long as you're doing it either in the upper hemisphere or in the lower hemisphere. Okay. If you do it in both the upper and lower hemispheres, the same coordinate will correspond to 2 different points. Okay, which is not good. Okay, so so in the upper hemisphere, that is these upper hemispheres. Okay, these are the generalizations of these upper hemispheres. So in the upper hemisphere, we want a mapping to Rn, which is defined as we simply get rid of the xi coordinate. Okay, like here, if you took the point xyz in the upper hemisphere, you simply drop the z coordinate and refer to it only by its xy coordinate. Okay, and this mapping is unique in the upper hemisphere. And you similarly do that in the lower hemisphere. Okay, you just drop the z coordinate. So the same xy, okay, in one coordinate system for the upper patch refers to the coordinates of this point. In the coordinate systems for the lower patch, the same numbers xy refer to the coordinates of this lower point. Okay, but these are different patches. Okay, and the important point is that these 2 patches, they have no overlap. Okay, these 2 patches have no overlap. Okay, so if we visualize on this S2, this uz plus and uz minus have no overlap. The equator is excluded. Okay, so uz plus is this upper hemisphere, uz minus is the lower hemisphere. The equator is excluded. Okay, from either of these patches. However, this definitely, if we only take these 2 patches, we would not get a chart. So we need to consider other patches. That is, we need to consider things like ux plus, ux minus, uy plus, uy minus. Okay, so that would be like the hemisphere, but now the hemisphere along the x-axis. Okay, so that would be ux plus would be like taking the hemisphere on this side, okay, again excluding this equator. This would be ux plus, and on this side we would get ux minus. Again, similarly, you could do the same thing for uy plus and uy minus, and only when you take all 6 of those, uz plus, uz minus, ux plus, ux minus, ui plus, and ui minus, then you cover the entire 2 sphere. Okay. But now what you can do is any, so for example, for the uz plus, I know how to get the coordinates in 3 dimensions by its embedding. And now I can assign 2D coordinates by just taking xy, and this is going to be a smooth map. Okay, sorry, this is going to be smoothly overlapping with any other coordinate patch. Okay, with the coordinates on any other patch that is overlapping with the uz plus patch. Okay, so let's draw the uz plus patch, which is this region. Okay, the upper hemisphere, and let's draw the ux plus patch. Okay, which is this region, this hemisphere. Okay, and on this hemisphere, a point P, which in 3 dimensions has an XYZ coordinate. Okay, in UX plus, I would refer to this not by its X and Y coordinates, but rather by its Y and Z coordinates. I drop the X coordinate. Okay, that is, I project onto this plane. How do I show this? I project onto this plane. Okay, so I project a point onto this plane in UX plus. So what is a point now? What is the overlap region between these 2 patches? The overlap region between these 2 patches is this region here. Okay, this quarter sphere. Okay, so on the quarter sphere, I want a mapping between one coordinate system and the other coordinate system. Okay, and I want to check that map is infinitely differentiable. Okay. So can you tell me what the mapping is? What is y in terms of these xy's, and what is z in terms of these xy's in that overlap region? Okay, let's do the first one. What is y in terms of x and y? So I want y as a function of x and y. What is this?
Sir, it is just equal to y.
This is just y, right? There's nothing complicated here. What about z as a function of xy?
It's equal to x.
Why? Z is not equal to x, right?
Sir, because it's a symmetry along this. Okay.
But that's not how we're assigning the coordinates. We're not assigning the coordinates by rotating the sphere.
So 1
You could do
minus
that.
x square minus y square.
Sorry?
Okay.
Yeah, Devashish, go ahead.
1 minus x square minus y square.
Yeah, square root of, in this region, the x coordinate is positive. So I can write it as 1 minus the square root of x square minus y square. Okay. If I had chosen the opposite hemisphere, I would take a minus sign, minus of square root of 1 minus x square minus y square. Okay. No. Okay, sorry. Anyway, we're working in this hemisphere. Okay, so let's take this. So in this overlap region between the patches, these are the transition functions. Okay, this is the transition function which takes me from xy to yz, and now I want to check that this is infinitely differentiable. Okay, this is infinitely differentiable on what domain? What is the domain on which I have to check the differentiability? What is the range of x coordinates and y coordinates? Sorry, what is the domain of x and y coordinates in this quarter sphere?
0 to infinity.
Why is it 0 to infinity?
Like positive x and positive y.
Positive x and positive y, but the x values are between 0 and 1, remember, right?
Oh, yeah.
Okay, in fact, they never reach 1, right? It's an open interval. So 0 less than y less than. Okay, so on this domain, okay, you can easily see that this function is infinitely differentiable. The problem would come at if x square plus y square is equal to 1. Okay, but in fact, yeah, so the other important point, okay, let me just draw this. If I take this to be x, this to be y, and this to be z, okay, and I take the overlap between, so we took the uz plus, which was the upper hemisphere here, and we took ux plus, which was this hemisphere, these two hemispheres. Okay, so this region on the sphere, okay, will map in the uz plus coordinate system. It will map to this region of coordinates. Okay, in the ux plus coordinate system, it will map to this region of coordinates. Okay, so in the uz plus, you are mapping to this region. Okay, and this region is in the interior of the S2. Okay, so in the interior of the S2, x square plus y square is less than 1, strictly less than 1, and we are also considering x greater than 0 and y greater than 0. Okay, so the coordinates xy over here, which we are assigning to some point here, okay, satisfy these two conditions. Okay, so now our transition functions, which are y as a function of xy is y, and z as a function of xy is square root of 1 minus x square minus y square. On this domain, okay, which is the overlap, okay, the coordinates of the overlap, on this domain, this is infinitely differentiable. For example, if I differentiate with respect z with respect to x, okay, it's partial z, partial x, keeping y constant, I get 1 over square root of 1 minus x square minus y square times half and times minus 2x. Okay, on this domain, as long as x square plus y square is less than 1, x is greater than 0, and y is greater than 0, this quantity is always well defined. Okay, it's non-singular. It doesn't blow up. This derivative is well defined. And I can go on differentiating any number of times, I'll get this to some higher power. But this will always be well defined in this domain. Okay, so you can check now that this atlas that we defined by defining these 6 hemispheres, okay, and just projecting coordinates from the hemisphere down to a plane, okay, that projection itself gives you valid coordinates which smoothly transition between each other. Okay, so this defines an atlas, okay, on a 2-sphere. So and the important point is that you need all of them. Okay, what would happen supposing I took only ux plus, ux minus, uz plus, and uz minus? What would be the problem with that atlas? Would it be an atlas?
No, sir.
Why?
So we'll have two poles at y-axis.
Yeah, the 2 points at the ends on the y-axis are not included in this equator and this equator, which I'm excluding from the others. So you really need to cover with all 6 patches. Okay, and once you cover with all 6 patches, then you have a full covering of the sphere, and you also have valid coordinates with valid transition functions. Okay, because they have to be infinitely differentiable, but remember they have to be infinitely differentiable only on the intersection or the coordinates of the intersection. Okay. Uh, okay, so anyway, I've just written this up in a little more detail here. Okay, now, so what we're going to do in the next class is, now that we have defined the idea of what we mean by a smooth manifold with a patchwork of smooth transition functions between local coordinate systems. Local coordinate systems are coordinate systems on a patch. The next step will be to exploit this smoothness, okay, to now do calculus on manifolds. So the next thing that we're going to do is, now that we have this idea of a manifold with smooth transitions, and locally things look like Rn, okay, we will now use this to now define calculus on an arbitrary manifold, not necessarily one that is just homeomorphic to Rn. Okay, so we'll be able to do calculus on spheres, torus, any arbitrary manifold. Okay, so that's it. We'll stop here. Any questions? I can take them. Sorry, I should just mention one thing, which I'll add in the beginning of the notes. This discussion is following Nakahara, chapter 5. Okay, and Nakahara is more exotic examples of manifolds that you can look at. The most of the manifolds that we study will be quite simple in GR.
Uh, Hello.
Yeah, hi Pravesh.
Sir, in case of sphere, Like, can we consider two patch, one excluding the North Pole and other one excluding the South Pole, and like in case of circle, can we cover the whole sphere?
Yeah, so like I told you in the beginning of the class, so if you do stereographic projection, right, so something, so imagine a plane which is sitting at the South Pole, let's say. So you can cover everything on the sphere except the North Pole by the stereographic projection. Similarly, you can do a stereographic projection from the South Pole, and you can cover everything except the South Pole. Okay, so this gives you basically with just 2 coordinate patches, you can cover the entire 2 sphere. So you don't have to use 6 coordinate patches. Okay.
Okay, so it is. I mean, it is valid choice of patches, no?
This is also a valid choice, and the stereographic projection gives you infinitely differentiable. So the transition functions between these 2 coordinate systems will also be infinitely differentiable.
Okay.
Okay. So, and also the other important point is that this choice of atlases, right, which is 2 atlases, which is 2 charts. Okay, let me call this U1, U2. So there's a U1, which is a transition. Sorry, I should really explain what U1 is. U1 is the entire sphere except the North Pole. Okay, the entire sphere except the North Pole is a patch on the sphere that is mapped to U1 prime, which is an open set of R2, and this open set just happens to be the entire R2. Okay. Similarly, on the South Pole, if I exclude the South Pole, then I get another patch which I'll call U2. Okay, and that U2 maps to an open patch in R2, which again is the entire 2-dimensional plane. Okay, it's also a valid open set of R2. Okay, so now basically my atlases are the set U1 and the map, that is the stereographic projection function. Okay, from this space U1 to a U1 prime, which is this entire R2. Okay, so this is one atlas. Sorry, this is one chart, and another chart is this U2 phi 2. Okay, and together this covers the entire sphere, and it has infinite. I mean, these transitions between phi 1 and phi 2 are infinitely differentiable. Okay, so this is one atlas. The other atlas that we chose had six patches. Okay, those 6 hemispheres. Okay, what I have not shown is that you can take the union of these 2 atlases, and that would also be a valid atlas. Okay, the non-obvious thing is to find the transition functions from one chart here to another chart using the stereographic projection. But basically, these members give you the same differentiable structure. These 2 atlases give you the same differentiable structure. Okay, and I think in fact on an S2 there is only one differentiable structure. So all atlases, any atlas that you choose is going to be compatible with the others.
Sir, is there any limit for SN, like how many patches we choose for given SN, then minimum number of?
Minimum number, no, but minimum number might be restricted by the topology. Like for example, S1 cannot be mapped to a single patch. Okay.
Yes, minimum
So
2 is required.
minimum 2 is required.
What
Okay.
was that formula? 2n plus 1 you wrote earlier?
That 2n plus 1 is basically for n is equal to n is, so 2n plus 1. For n is equal to 2, this was 6. Okay, this is just the number of patches. This is 6 hemispheres. So for an n-dimensional sphere, it's 2n plus 1 patches. Okay, it's basically the way I got 2n plus 1 is there are 2 hemispheres, and n plus 1 is because basically for each coordinate x1, x2, x3, right, I can choose one axis and then kind of split into hemispheres along that axis. So in n plus 1 dimensional space, there are n plus 1 axes, and there are 2 hemispheres. So that's how that counting came out.
Okay.
All right, if no more questions, let's stop here and we'll meet on Thursday. Okay, and sorry, one more thing, the first assignment on Rentala observers has been posted. I think the due date is in about 2 weeks. Okay. Okay, see you then. Bye-bye.
Thank you.
Thank you, sir.